Hello and welcome to this webinar of how FASTSUITE E2 changes offline programming with the integration of data continuity and artificial intelligence. My name is Israel Montoya. I am your host today. I am part of the product support team here at CENIT, and I'm going to show you how two ideas revolutionize the way we think about offline programming. The first one is data continuity. So how do we make sure that our process reflects the design all the way from the beginning to the end of the programming? And the second one is how AI can help us to make the optimization and highly reduce the number of hours and the tedious programming and help us reach the available limits of the quality of our process. This is the agenda we're going to cover today. We're going to start a little bit with what is the data continuity in the arc welding process. What does it mean to take a design and making sure whatever you put on the design board and whatever was intended for a part to be reflected all the way to the end of the process, and how do you make sure that this happens, and what are the possible pitfalls that lie in the middle. The second one will be how this data continuity is ensured within our FASTSUITE E2 software, and what are the strategies that we're following and the new systems we're creating, interactive and automated, to make sure this data continuity is kept in place. Then we're gonna move a little bit on to the burden of interactive path programming. This, we're gonna make a quick exploration of how interactive offline programming has been the norm during all this time, and what are the shortcomings of the interactive way of teaching for an offline program. So what are the major issues with interactive programming, including how it can be repetitive and how it can be sometimes challenging for some people. Then I'm gonna show you our solution to this problem, which we call the automatic toolpath optimization, or APO for short, for the example of 6-axis arc welding. We're gonna see what it does and more or less how it works. Then we're gonna move on to understanding the settings for this APO, so you can actually go and work with it directly, and then you can be sure what are you doing. And then some of the best practices for our new APO technology. At the end, we're gonna quickly go into the advances that we have for automatic toolpath optimization. Also for laser cutting processes. Quickly, we're gonna have a glance just for the customers that are more interested in the laser cutting process. So thank you very much for joining us today, and I hope you have fun, and then you're also interested in seeing some of these new ideas that are coming towards offline programming. So what is data continuity for the arc welding process? Well, we have to start thinking by how is normally the process of manufacturing a part is taken towards the beginning, from design all the way to the end to get a final part made. First of all, you begin by creating CAD data. So the CAD data contains the plates and everything that's going to be the final part. And along with this, it's also designed where are the welds going to be placed and what size or what properties they need to have. On a separate side, we would also have our welding experts deciding what settings would be for the welding machines to get those settings correctly. So let's say for a 10mm weld, how much voltage, how much current, what is going to be the amount of wire feeding that you need. And all this process is somehow stored into the tables for the machines, depending on how big you want a weld or what position is this weld going to be performed on. Many times this kind of knowledge is acquired by doing testing. So taking similar plates, doing some feasibility testing, and then making cuts and ensuring that the quality is what we are expecting for a specific part. Then we have to somehow match the design that we want for the part. So we have to match this specific weld positions and weld sizes to the parameters that we want to have for each one of the parts of the welding equipment. Until now, even for offline programming, it is common that you will have this process be made manually. It is common that a robot programmer will come and then it will take the CAD data, then it will try to read some prints or try to read some schematics for welding, and it will try to decipher, okay, we need a welding with these characteristics in this place. I'm gonna make the robot move in this section, and then I'm going to set the parameters according to whatever it is necessary to create this weld. You can already start seeing the problem with this strategy. The first thing is that humans are not 100% reliable. So it is very common, especially when you're getting big parts. So you're getting parts where you have dozens, sometimes hundreds of welds, that someone makes a mistake, that someone comes in here and it decides, oh, this is the weld that I need, and reads the sign wrong, or creates sometimes the correct weld in here, but it does not select the correct parameters for that weld. And normally what happens is it's hard for someone to notice that this problem is happening in the first place until you get to the final part when you create a program for the robot. You try to weld it and you don't get the quality that you're expecting. Then you will have to trace back and have some kind of investigation about what is happening. And luckily, you will find that there was a miscommunication, so the data was not preserved. Someone made a mistake in the part, either someone who printed it wrong, either someone who read it wrong, or someone then clicked the wrong button. Many times this could also happen because the interfaces that are in the robots do not necessarily match what we want for a welding process. So that means that the angles don't have the same name, or we don't have like a welding schedule, or like the same symbols in the prints and in the software, and all these kind of things can lead to some of this data to be lost in the process. The worst case scenario is that we do not notice immediately that some of these parts are not getting the quality that we want. Like, let's say if there is a slight deviation, and then we can really start losing a lot of money, because eventually someone will realize that the quality that we're getting, the resistance we're getting from the welds is not ideal, and we're going to have a recall, and this can be a really, really huge problem. So how do we tackle this? This is where it comes the idea of data continuity. So the concept of data continuity is try to use the same information that we created and somehow migrate it into our other systems. So make the data compatible from the design, from the process feasibility, all the way until our end program. Right? So instead of having to rely on humans to translate this or trying to make it match as appropriately as possible, we make sure that our systems match by default. So we're using the same language, and we also have the option to import this in a common understanding from all the systems. This is what we mean from data continuity. So changing our systems to match our data instead of trying to rely on people always getting it right 100% of the time, because that's not a good idea. So what is our idea to keep data continuity ensured on FASTSUITE E2? We're going to take the specific example of arc welding in this case. And we're going to show here what we call the arc welding cockpit. So you've probably already seen some of the demos that we placed before, but I want you to have a deeper understanding of why is this such a valuable feature for a lot of our customers. So first, we're going to begin with our controller section. Here now in our controller, we have a section called a process table. This process table is designed to gather the same amount of information that you get out of our welding testing. So many times you will gather this with experience from the welding process. And here you can see, okay, if I'm making a certain welding type with a certain size and a certain position, then I'm gonna need this speed, I'm gonna need this wire diameter, voltage, current, and all of the different settings that are necessary to create this particular weld that I want to achieve. We can of course customize how many things are shown here and how many of these are we going to use in our final program. But the idea is then you gather a database, so the same database that you are creating for your programming schedules, to be translated into the software. So we don't want you to do this manually. The idea is then you create a CVS table, and then you will import it directly into the software with whatever hundreds of types of welds that you have proven, tested, and then you know it works with the right settings that you have gathered with your welding expertise. So this is now integrated into the software as part of the controller. So this is the first step. Then you now have gained the knowledge of all this welding process inside the software. The second part comes in your welding definition. So there is two ways to create the welding definition. One, it can be manually. We're going to explore first this one. And then the second one can be automatic, coming to try to preserve even more the data continuity. Let's say you get your CAD data. The first problem would be the users have different language or a different way to talk when it comes from the robot or when it comes from a welding specialist point of view. We have now changed this by redesigning the way that we define our process geometry. We have now, within our process geometry, what we call the arc welding cockpit. And in this one, you can define in a more similar way to what you would do directly in a welding print. So you can just copy this one-on-one. So you can here define a material ID, the type of material you're working with, the size, the position, if there is going to be a push and pull, the type of weld, and you will have a sign similar to what you will get in a welding print. It is easier for someone who's not experienced into robotics to just fill this table because you're basically just entering the same thing than you will get in a welding print. And when you define the process geometry, you will have this data alongside here in your process geometry definition. The second part of doing this is if you have the possibility of defining your welds within your CAD, you can also export this information with our open XML format. So that means you can bring this, make a parser for this, and then import the information with this format about where the welds are, about not only the CAD information, but also where are the welds located, and all of this other stuff that we are generating before. So whoever it is designing how big the welders have to be can do it from the same time that you are designing the CAD, and at the end just exporting this information. It will all come together. Now, when this joins together, and the great part of this is that we can now merge the information, the intelligence that we have from our welding database to the specific weld that we need to create. So that means when we decide, I want to program this process geometry, it will automatically figure out what is the material, what is the size, or what is the welding position, and it will assign the correct settings for the welder program, or if we need to define current and voltage, or whatever are the settings that we need to create in here, it will automatically gather those and set them into our active program. And from our active program, we can get them out anywhere we want to our final program. So with this, we're skipping the part where someone has to go manually and decide, okay, this weld is this size, I'll have to give it this, and automating all this process, but most importantly, ensuring there is no mistakes. And since quality is one of the most important things for our customers, and also saving money and not having to do any kind of recalls or having to do excessive testing, or simply not being sure that the data has been preserved and there is a mistake, there might be someone who did a mistake in the process. This makes way easier to do an audit over the process and the part to make sure that anything that we design will be kept all the way until the output, that is the program, is going to run in the robots and it's going to select the settings for the machines. Next topic that I want to talk with you is what I'm going to name the burden of interactive path programming. Offline programming, it is certainly better than manual programming. It solves a lot of problems with collision detection, and it gives a lot of features for the user, and it opens so many doors. However, it has its limitations. And one of the biggest limitations is when we start working with big programs. We start getting into some small problematics. And the first of all is that a lot of time is spent trying to make the path optimal. So that means not simply to take the robot and make it move along the path, but making sure that it's not colliding with anything, that the path is 100% reachable. And when we have to compromise, so that means in the sections when we have to modify, we have to deviate from the original 45 degrees, that we make sure that we deviate the least amount possible. So for most users, actually, this is the part that it takes the most to master. So the first problem that I want to address here is for a user to get to this point where they can do it, this is probably the part that is going to take the longest to learn. Because you need to have a little bit of foresight of which way you need to modify, which are the angles that you need to change, if you need to make an interpolation, if it's better to make like a modification in only a couple of points or a full interpolation, several different things that you need to learn. And it's probably the section that is going to take most of the users the longest amount of time to learn. It is not that it's too complicated, but it is like one of the barriers for many times someone who is experiencing welding and is trying to move now to understanding like robot kinematics or optimizations and paths and targets, base frames and all this kind of stuff. So it can be a little bit intimidating. The second part is like, paradoxically, once you learn how to do this, it becomes a little bit boring because many times the optimizations that you have to do are basically the same. So many times it's just modifying a couple of targets, some degrees, rotating the torch a little bit, and then you will have a path that is reachable or is not colliding. So both of things are not great because the first one, it is taking the users into a zone that they're not very comfortable starting working with the new software. And the second one, it makes it that if you have a program that is very big, let's say a couple of dozen welds, sometimes hundreds of welds, most of the programming time will be taken by doing these simple changes, by doing these optimizations. Another problem that is even more concerning is many times when someone is creating these optimizations, we have very little way to know if this is the best optimization that is possible. So that means, sure, we are modifying these targets. They are now not in collision and they do not have problems with unreachability, but have we modified them too much? Because we have to take into account that every degree that move away from the ideal, let's say 45 degrees of the path, is going to be a degree that we're not going to have an ideal process, or whatever it was designed before. It's a section where we're going to be compromising in order to be able to reach the desired weld. And we have to do it. We have to compromise because at the end of the day, we need to make the weld. But we cannot be sure if that was the best solution or the solution that had the minimum amount of compromise. Why? Because many times the way that these results are reached is an iterative method. That means we come, we modify a little bit, we see if we reach, then we come and we modify a little bit more. And then when we get a result, we say, oh, well, this is the result that we get, and this is our path now. Maybe there is an intermediate result that can make 2 or 3 degrees difference, and it might not sound like a lot, but sometimes that can mean the difference in between a part that reaches certain level of standards and what should it be able to resist or achieve. So our response to this now is what we call our FASTSUITE E2 automatic toolpath optimization, or APO for 6-axis arc welding. And I'm going to try to explain you quickly here what it does. So in a nutshell, what we're doing is something similar, you could say, to what a user would do, is we are searching for an optimal solution for the toolpath elements. So we basically go to each one of the toolpath elements that we have in our path, and then we create a variant space, what we call a variant space. Basically, this is just a multidimensional array of different variations of a toolpath element. These variations are created based on the different possibilities that we have to modify our toolpath element. So that means we can change the tool angle, the work angle, and the travel angle. So our goal is to reach a position of the toolpath element where we do not have any collisions and where it is reachable for a robot. Of course, in this variant space, there is many combinations of these different modifications that will give you a result that is viable for these requirements. So then the next task is to sort these variants in a way that we can decide which ones are the ones that we get what we call the less cost. So the process here is using some form of artificial intelligence. What we are doing is searching for the variants with the lowest cost. If you're familiar with some topics in artificial intelligence, this is just a form of saying which one is the most optimal solution from all this variant space that we have. We use different methodologies in the background to trying to find the best possible path. And we evaluate, but also how is the transition going to be in between one toolpath element and the next one. And we also evaluate in an iterative way. So that means we make sure that everything that is in between the toolpath elements, it is also taken into account for those parameters that we're given. If there is any problems in between the path, we also take care then make a second iteration, maybe add extra points or maybe modify the points that we have in order to get a result that is viable for the parameters that we're looking for. Our artificial intelligence basically is just looking for what is the absolutely best solution from these millions of possible variants that we are working with in the background. So instead of the user manually searching for different variations and how the toolpath should be modified, we go through all of the valid variations within a range for this variant space, and we find the one that is the best suited. First of all, this automatic toolpath optimization is going to give you a result that is going to be the best suited. So you can be sure that whatever is the most optimal result for a specific toolpath is going to be taken into account, and you are going to get it without needing to search it manually. So that means for the advanced users, you will not need to spend so much time making the same modifications over and over again over the same number of targets. And for the beginner users, you can see what is the ideal modification and how to do this or what should be expected from the software. And it will give you more confidence in case you want to modify something manually or see what is the expectation of the best possible outcome. And it will also eliminate for the big programs a lot of this repetitive task where you only have to modify a couple of degrees, and it will give the users that time for other very important tasks in the process. So I want to now walk you through this. How are the settings actually working, what they do, and how do they interact with the software, as a little bit of a small workshop for understanding how does our Apple actually goes and solves, and how does it uses the settings to create an optimal result. So you can download this example and actually try it for yourself. We have a couple of different robots and brands and examples that you can try. So please connect with us so you can, if you want to try this yourself. But I want to go through the what we call the evaluation criteria and the different things that you will see here with this automatic toolpath optimization. So everything is going to be when you click in our active program, in the main program, and then go to toolpath quality. The first thing that we see is the evaluation criteria. So first of all, we're always going to check for unreachability, collision, and singularity. So that means that we have to set up the collision sets for our workstation. I would say that you should probably do that always, because you should always check for collision sets. That's one of the main benefits of OLP. But just to double confirm, you always have to have here collision sets within our settings, and making sure the collision groups, in this case, in between the torch and the workpiece or the robot or the different things that you want to optimize, are connected properly. And the first thing that we're going to check is our 3 angles. So how are we going to evaluate the work angle, travel angle, and tool angle? And for each one of those, we will have different zones. We will have green, yellow, orange, and red zone. And these are basically linked to how much can we compromise our process. And the default settings that we have set here are actually pretty similar to what you would use from Arc Welding. And a lot of things here actually should work automatically, but it's important that you kind of gain an understanding for now of how are these linked to what we see happening in our optimization process. So it's not just magic, it's how are these working in the background. The first green region is the range of optimization that doesn't cost anything. So that basically can be modified freely by the robot. In the arc welding process, we are putting this at 1 degree. And this is kind of critical because anything about 1 degree, it starts to compromise the toolpath a little bit. The more it is, the more modified it is, the more compromised is in the toolpath. So in this case, we're establishing one range in between 1 and 10 degrees, which is the yellow section, that we are saying you can modify the target in between 1 and 10 degrees. And this is going to make it less optimal, but it is okay to optimize it within that range. The same we're doing for the other travel angle. So both for the work angle and the travel angle, we have these settings. The next one is the orange section. So the orange section is, you can go into this orange section, but it's not preferred. That means the cost of modifying and passing this, like from 10 to 30 degrees, is way higher than just the normal modification section. Because for most of the process, the normal modification will go somewhere in between 1 and 10. And in extreme cases, which we do not want, we can go somewhere in between 10 and 30. But if you have some experience with welding, you know that this modification is not great, and it should only be used in extreme scenarios. So that means we're going to try to stay away from the orange section, but only in extreme cases. If we do not find any solution without the yellow section, we will start going into that orange section. The red section is like anything above 30 degrees is not a solution. So that means anything that you find above that section, it is pretty much unusable. So something else needs to be done, and just if you decide, you can abort the calculation. And this is the ranges that we have for the travel deviation. And if you're familiar with this, like you can see then 1 to 10 also for the travel angle from push and pull, it is reasonable. Anything from the work angle, when you start getting out of this range, somewhere in between 10 and 30, you're really degrading the quality of the weld, because you're eating too much into one plate. You might need a specific set of settings on the welder. You need to do some extra stuff. And above that, you're probably not even welding. The last one is a bit special. So this is the tool deviation. So that means how the robot is going to rotate out of the set axis of the tool. That means that for most of the single torch, this is pretty much free, because pretty much all 360 degrees are valid solutions for this one. So by default, this one is not evaluated. So that means anything here is not taken into account. So you can modify this one as freely as you can. and is only going to focus on keeping the other two with lowest amount of overall cost and deviations and transition in between points. So everything that we're taking into account. If for some reason you have a preference of how this angle should behave, so that means if you program this and if you're trying to keep the torch in a certain angle, then you can enable this. You can enable this, and it's also going to take into account, from 0 to 45 degrees, it is okay. From this 145 to 180 is like not so good. And more than that, that means you're probably changing configuration of your robot. So not good. But then again, this is your choice, and you can select here how much you are able to deviate. And you can also control this for other processes like tandem. So for example, in tandem, you can evaluate this and you can say, you know what, my maximum deviation is like 2 or 3 degrees. And the limit where I have is like around 5 or something like this. So processes where the alignment of your tool requires you to do not rotate too much. Access limit proximity, this is just so you do not get too close to the limit of your robots. So basically here it says like you should be anything below 5 is fine. We have the green section here, so anything between getting the 45 degrees limits to the 5 is fine. When you are getting to the 5 and 1, you start getting some increased cost into this. And if you are getting into between 1 and 0, this is very dangerous. So you should try to stay away from it. The same goes for axis speed. So you wouldn't shoot above what is decided for to be the 100% speed. Once more, probably the settings that come here by default are going to be enough for you to create a process, especially if you're doing it for arc welding. We have created these settings for you to be able to use this as come out of the box. And the only thing that you might need to modify is the enable the tool deviation if you have a process that needs to conform to a specific predefined tool angle on the set. The next one is the variation space. You're probably never gonna modify this, but this is what I was talking before. What we create is this multi-dimensional array that we call variation space, where we create several different variations from the target 1 degree space with certain settings, and we keep it here for our internal control. The last one, and most importantly, is the optimization control. So here, one thing that I would suggest is that your toolpath optimization, you have 2 sections. So you can go on quality or in speed. And many tests that I have done, I would always place the quality somewhere around 3 to 5. And this is basically a percentage of how much time do you want to spend doing the optimization and how many searches the artificial intelligence algorithm is going to use in order to find the optimal solution. So that means if you put it all the way to 100, it's going to find a solution, but it might not be the most optimal solution. And if you put it all the way to 0, it's going to find the absolutely most optimal solution. And what I have found that it gives me very good results, it's somewhere around 3 to 5. Now, I must say this doesn't grow linearly. So from the 0 all the way to the 100, you should see a change more or less of 3 times. So this takes 10 seconds. This will take around 30, just as a frame of reference. But what I have found is very good to use it somewhere around 3 to 5. Override collision tolerance. It will give you the possibility to have extra tolerance for your collision detection. So that means you can not only go directly scraping your torch into your metal, but if you enable this, you can add an extra couple of millimeters where you can say, you know what, I want to have at least 2 millimeters in between my torch and my part. This is just for taking into account small deviations of the part or small differences of your torch. If you see a section where this could be critical, I would say enable it, and normally somewhere between 1 and 3 millimeters does the trick in here. The last part of the settings comes with this motion check. So this motion check, it does like a iterative search for seeing if the optimization that has been created is valid not only for the toolpath elements, but it's also okay for the rest of the toolpath. So that means if you go in sections that are long, it does not only modify the beginning and the end, but it checks something in between. So in the cases where you have a collision or you have some problems in the middle, it will also try to solve it. This works hand in hand with the insert process points. If you disable the insert process points, you will simply modify the targets that are existing already a little bit more. And you will need to see if your toolpath is short. Maybe this is the right thing to do. Maybe it's just to disable the insert process points and just, compromise the toolpath in general to keep the consistency. But if your toolpath is long and you only have compromises in very small sections, you want to insert extra points. So only small sections of your toolpath have like a decreased quality, and most of it keeps the highest level of quality. You can decide if you want to insert more points or not, but I would say in general, the motion check is always something good to have. The motion check by default has some settings that it will check every 1 millimeter and every 1 degree of motion of the robot. I would say for the process that I've seen, this is working perfectly fine. And for the inserting process points, it needs at least 10 millimeters. And this is what I was saying, that you need the space to insert these extra points. So if your toolpath is small and if you're seeing some sections where it might have a collision in between, just disable the insert process points and have an overall change. You can have this by default. And in the very long paths where you have like tiny collisions in between, then you can insert the process points. There are some things in here that I just have to mention quickly for the sake of understanding how this works in the functionality. It is that you always get a progress bar when you're creating this optimization. You would always get a report that it will tell you how many collisions have been solved and what is modified and the time that has been taken for this optimization. You can always optimize individual operations or the whole program. And if you don't like something, you can always go into your toolpath and delete the optimizations that have been done automatically. In the future, we will move away from many of these settings into some more process-driven settings. But at the moment, we want you to understand at least what do they mean and how can you modify and tune in your automatic path optimization. But in the future, many of these settings will be chosen automatically depending on the toolpath that you're handling or in the process that you are doing at the moment. After this, I want to mention some of the best practices that are required for making this app work correctly. And some of this is just things that you would have to do anyways as a good practice with your project. For example, you need to set your axis limits and your axis speeds properly. So if we're optimizing for the limits and the speeds in our app, of course, this has to be also set correctly in your resources. As I said before, you also need the proper collision groups. So you can have collision groups connected within your torch and maybe discard from here anything that is not completely relevant for the process, because as I said before, this whole thing is evaluated. So if you are only taking care of the robot and the workpiece and the torch without other stuff, it will make the calculation a little bit quicker. And you can also exclude the tip of the wire because that one shouldn't be taken into account for the collision detection. Our automatic toolpath optimization is at the moment supporting the use of external axes, so you can put as many as you want, but the only restriction is then you need to define it every time that you're changing. That includes the beginning, so you need to define the very first point with the values of the external axis. One last thing that I want to mention is regarding the automatic toolpath optimization for laser cutting process. So automatic path optimization was originally launched from our side with the laser cutting machines, 5-axis laser cutting machines, and now we extended towards the Arc Welding 6-axis. But we are still improving the 5-axis, so that means the features that you've seen here, the report, the progress bar, the control with the toolpath dashboard for deleting modifications, they're all available in the laser cutting as well. So we're improving both of them side by side, and also the enhancements for intermediate point check and for creation of new points is one of the features that we have also launched as well for the laser cutting machines. So all of these things that have been now enhanced and improved on the side of Arc Welding are also available for the laser cutting machines. We're very proud of it, and for taking a step forward towards what we believe is the autonomous programming and the way that is going to be made in the future when the program is pretty much completely, fully autonomously created by the software. That's all from me from this webinar. I really appreciate your time for listening to me and for giving a chance to the software. Please, if you have any questions, just talk to us directly. We can easily give you a demo about the software, talk about your specific case scenarios. And if you want, you can also follow us on social media. We have some different channels where we give some updates and where we will have more trainings or webinars or new features that are coming and all kinds of new stuff. So if you would like to, we will link here as well the social media that is available for you. Thank you very much again, and we see us next time.